Okay, Algebra 2 fans, our topic for today is we're going to graph rational functions. And before we start, let me give you your joke of the day. What do you call a group of disorganized cats? The answer is a catastrophe. All right, we're going to do three things here. One, we're going to graph rational functions. We'll take a look at what they look like. We'll state the domain of the rational functions, and then we'll find vertical and horizontal asymptotes. So first thing, let's look at the graph of a rational function. The definition. Now, we've looked at a lot of polynomial functions. We've looked at exponential. A rational function is in the form r of x equals p of x over q of x. P and q are polynomial functions. Q is not equal to 0. The domain is the set of all real numbers except for where the denominator is 0. So what's going to make this different from a polynomial function is that you will have variables in the denominator. Now, one thing to think about, when you have a fraction, you can never divide by 0. So if that happens, then the function is undefined at that place. Okay, so as an example, f of x is equal to 2x over x minus 3. Now, I've already graphed it for you. Okay? And you can also go onto a calculator, you can graph this, and you'll see that you get the same thing. Now, there are a couple things to notice. First of all, there's two parts to the graph, both curves. There's this curve here that is going downward, and then it looks like it kind of jumps. It comes up to here, and then it starts going down again. But you'll also notice that you have this dotted line going up and down, vertical, and you have another dotted line going left and right. Okay, so I'll explain what that is in a couple of minutes. The domain of this function, well, it looks like we're going to the left here, and we're going to keep going. That arrow tells us we'll keep going. So it looks like it goes to negative infinity. Now the x values keep going. We go to the right. But then we hit this vertical line. And what happens, and what is happening here, this graph is going down, and the curve is going to get closer and closer to the vertical line, but it's never actually going to get there. Now, this vertical line is what we call an asymptote. Okay, A-S-Y-M-P-T-O-T-E. That's an asymptote. That is a line that the graph is going to approach but not actually touch. And so this one's a vertical asymptote at x equals 3. So what's happening here is that the graph is going to get closer and closer to 3, but it never actually touches. And the same thing on the other side. If I come up here, the graph is going to get closer and closer to that vertical line, x equals 3, but it's never actually going to touch. So what happens is that my domain is not negative infinity to positive infinity. My domain goes from negative infinity to 3, and then from 3 to positive infinity. It's going to be everything. I'm going to say the domain is all real numbers except 3. Now, what makes 3 so special? Well, if I take 3 and I substitute it for x into the function, if I do f of 3, I get 2 times 3 in the top, 3 minus 3 in the bottom, which is 6 over 0, but you can't divide by 0. That is an undefined situation. So what that tells you is that the graph does not exist. The function does not exist when x is equal to positive 3. So for my domain, I could substitute any other number except for 3. So you can write it like this. Another way that you'll see it is as a set, where we'll say the set of x's, and then a slash, x is not equal to 3. So the way we read this is the set of x's such that x cannot be equal to 3. Now for the range is the y values. So it looks like our function is going down to negative infinity, and that will continue. But as it comes up this way, notice that it starts to kind of flatten out. And it looks like it's getting closer to the horizontal line. it'll keep getting closer, but it's never actually going to get there. It's never going to touch. Now that line is y equals 2. That's a horizontal line. That is what we call a horizontal asymptote. So horizontal asymptote. So what happens is we're never actually going to get the y value to be 2. Above the asymptote, you'll notice that this graph is going to keep going up. So for the range, any y value will give you a point on the graph except when y is equal to 2. So the range, we're going to say the set of y's such that y is not equal to 2. Intercepts, well, x-intercepts, do we cross the x-axis? Yes, we do, right here. Now that's the origin, so that would be 0, 0. The y-intercept is going to be the same point, 0, 0. Increasing and decreasing. Well, as you move left to right, okay, imagine yourself, you're on a roller coaster. This part is going down. That's decreasing. Now when we jump over the vertical asymptote, suddenly I come up here. This is still decreasing. So what happens is, in this particular graph, there is no increasing. So none. As we go left to right, we're never actually going up. Now we are decreasing though. So the first interval where we're decreasing is going to be all of this section right here. For all of that, the function, the graph is going downward. So for the x values, that's from negative infinity until we get to positive 3. So decreasing is negative infinity to 3. And we can put the 3. We're not including that. We're just saying that from negative infinity until we get there, the function will be going down. The other part where that's happening, though, is up here. So that section, all of this is decreasing. So from an x value of 3 all the way to positive infinity. So also 3 comma infinity. Vertical asymptotes. Well, the vertical asymptote is x equals 3. The horizontal asymptote is y equals 2. Now as for the end behavior, this is going to be a little bit different. As your x values go to negative infinity, what's the function doing? Well, as x approaches negative infinity, as we move left, this curve is going to get closer and closer to 2, but it's never actually going to get there. But what we'll say is that the y value, that's f of x, is approaching positive 2. So as we go to the left, what's the y value doing? It's getting closer and closer to that value of 2. As x approaches positive infinity, the function, as we go to the right, the function is coming down. It's getting closer and closer to this horizontal asymptote, but it will never get there. So what's it approaching? The y value is 2. Let me show you how this is working here. If we take a calculator, let's go to y equals. Now, when I type this, I'm going to put the whole numerator in parentheses, 2x. I'm going to close it, and then divided by, I have to put the whole denominator in parentheses as well, x minus 3. Now if I go zoom 6, let's take a look at this, and we'll see the picture. Now what you'll notice is that they don't actually draw the vertical asymptote or the horizontal. That's fine, but what we know is that it exists. If I go to the table now, first of all, notice that when x is 3, the y value is an error. That's because the function is undefined at x equals 3. It does not exist. So that's why we exclude that from the domain. Now as I go towards negative infinity, as my x values decrease, look at what's happening with the y values. 1.6, 1.64, 1.7. What happens is that we're getting closer and closer to 2, but we're never actually going to get there. Okay, so we're not going up to positive infinity, we're approaching 2. Okay, so I'm going to stop. If you keep going, you'll get to 1.9 and so on. Now, as x approaches positive infinity, so let me come back down here. as your x values get really big, notice the values are actually decreasing this time. 2.85, 2.75, 2.6. Now look at what's happening. We're getting lower and lower, but we're getting closer and closer to 2. We're never actually going to get to 2. So 2.08 and so on. So we'll keep going down. So this is your end behavior. You're getting closer to 2, but you're never actually going to get there. Okay, so for vertical asymptotes, if you are looking for a vertical asymptote, what you're looking for is where the function is undefined. The function's undefined when the denominator is equal to 0. So if your denominator, if the bottom of the fraction is equal to 0, then we know the function's undefined. That would be a vertical asymptote. That does not exist. You cannot divide by 0. Okay, so in the directions here, state the domain and vertical asymptotes of each function. Graph each function on the calculator to verify your answers. We don't need to graph it. Let's go ahead and just figure this out. For the asymptotes, you just focus on the denominator. When is 2x minus 8 equal to 0? What would make that equal to 0? Well, let's solve an equation. Plus 8 plus 8. So we get 2x equals positive 8. Divide by 2. There's a vertical asymptote for the line x equals 4. If I plug in a 4 for x, I get 2 times 4 is 8 minus 8. I get 0. I cannot divide by 0. That's undefined. That is where we would have a vertical asymptote. So if you were graphing it, you would draw a vertical line where x is equal to 4. Just to show you y equals. Let me take 3 divided by parentheses 2x minus 8. All right, there it is. Now you can see it looks like there's kind of a vertical line, 1, 2, 3. There's x equals 4. So again, they don't draw it for you on the calculator, but it exists. So we never actually get to x is equal to 4. All right, let's take a look at number 2. 1 over x squared minus 9. A vertical asymptote is where your denominator, x squared minus 9, is equal to 0. Well, we could factor this. That would be x plus 3 times x minus 3. There's actually several ways that you could do this. I'll factor it. Now, I'm looking for where the factors are equal to 0. So what I do is I take the first factor, set it to 0. Take the second factor, set it to 0. And then we'll solve it. We'll go minus 3 on both sides. X equals negative 3. Here we'll go add 3 to both sides. We get x is equal to positive 3. So the domain, we'll have vertical asymptotes in these places right here. If I want to write the domain, what I can actually say is d equals the set of real numbers, okay, the set of x's such that x is not equal to negative 3 or positive 3. For number 1, I can go back and I can write that. The domain is the set of x's such that x is not equal to 4. All right, so let's do the last one here, number 3. Again, it's a factoring problem. It's a trinomial. Let's go ahead and factor that. I'm going to set that equal to 0. I'm looking for two numbers that multiply to negative 15 and add up to 2. And my combination will be positive 5 and negative 3. So that's x plus 5 times x minus 3 is equal to 0. Now what I'll do is I'll set the factors to 0, and if x plus 5 is the factor, I'll get x equals negative 5. And if x minus 3 is the factor, I'll get x is equal to positive 3. Okay, so I skipped a couple steps there, but it's the same process that I just did in this one. So the domain is the set of x's such that x is not equal to negative 5 or positive 3. Now you'll notice the numerator does not tell you about the asymptotes. It doesn't tell you about the domain. But if I put a 4 in for this, I would get 0, and that would actually be the that would be the solution. That would be the zeros of the function. So we're going to stop right there, pause the video. That's the end of part 1. Go ahead and flip it on the back and go to part 2.